Okay, so like I said, in Calculus 2, you studied some differential equations, and you had like dy, dx equals some function of x and y, and if the differential equation, if you could separate the variables, you could solve the differential equation usually, y as a function of x. So we're very interested in solutions to differential equations, if we can get solutions. Well, in section 5.7, we don't look at one differential equation, but we look at a system of differential equations, a system of linear differential equations. So a linear differential equation, you notice like here, if, let me see here, one moment. If you look at the first differential equation, x1 prime, that means dx1 dt, by the way. x1 prime is equal to a linear combination of x1 up to xn, and the coefficients of x1 up to xn are numbers. So that is what a linear differential equation, all the differential equations, okay, and there are n of them here. There are n of them. All of those differential equations are constructed as such. And if you do that, we call the system a linear system of differential equations. Now, what we can do, you see, is we can represent this linear system of differential equations by this matrix differential equation. The vector x, we're going to take the derivative of the vector x, which is a function of t. So an x of t is defined as this vector. So if you define x of t as this vector of functions, x1 of t, x2 of t, up to xn of t, then if you take the derivative of that vector, that's equivalent to taking the derivative of each of the functions, x1 of t, x2 of t, up to xn of t. So you get x1 prime of t, x2 prime of t, up to xn prime of t. Those are your entries in the vector. And then, of course, the matrix A consists of your coefficients of your variables, x1 up to xn. So you can represent this linear system of differential equations by this matrix differential equation, where it's understood how x of t, okay, and x prime of t and a are defined. Okay, are there any questions with that notation? Are you okay with that? Are there any questions? All right, so far so good. Okay, well now what we want to do is we want to be able to figure out, hey, what's a solution to this system of differential equations, this linear system of differential equations? Is there a solution to that? And if you remember, when you took differential equations, when you took Calculus 2 at Montgomery College, you started off by making some, the book would give you some solutions to differential equations, and you could prove those are solutions by showing the differential equations, by showing that they're actually solutions, that they actually work in the differential equation. Okay, so like for instance, let me do an analogy here. So like for instance, if you have y prime equals y. Okay, that's a little differential equation there, right? Y prime equals Y. Well, you could say, is Y equal to e to the t? Is this a solution? Is this a solution? Well, all you need to do to check that is take the derivative of y. The derivative of y is just d dt of e to the t, because we're saying y equals e to the t. That equals e to the t, and that is equal to y. So the answer is yes. This is a solution, and we showed it by doing basically a check. This is a check, right? The solution checked out. So that's one way of showing that you have a solution to a differential equation. Okay, I mean, if you make a good guess and it checks out, you have a solution. How many recall that when they learned about differential equations in Calculus 2? Those kind of little problems. Okay, very, very good. Well, let's now look at linear algebra. What could be a solution to a linear system of differential equations? Okay, well, what could be a solution is something called an eigenfunction. An eigenfunction. Now, what I'd like you to do is take a few moments to copy this example down, and then we're going to go over the solution. It will be fairly quick. We might run a few minutes over. We might run 5 minutes over time, but it won't be more. If you can stay, I'd appreciate it. If you can't, it'll be on the recording, but try to stay if you can. Let me give you a moment to copy this example down. Okay, so what we're doing here is we're letting lambda be an eigenvalue of A, and the vector v be its corresponding eigenvector of A. We want to show that this here, we want to show that x of t equals the eigenvector v times e to the lambda t is a solution to our system of linear differential equations. I should probably call it instead, class, let me call it the linear system. I want to make sure my terminology is correct here. Let me just, yeah, it is a linear system. Let's make that correction. A linear system of differential equations. All right. So I'll move to the solution when you're ready. You've copied it down. Okay, does anybody need a little more time to copy, or are we good? Don't want to rush anybody. Sega's good, Robin's good. So again, we want to show that this eigenfunction, this is called an eigenfunction here. When you take the eigenvector and multiply it by e, the scalar, or the scalar function, e to the lambda t, the function of t, right? We want to show that that is a solution to the linear system of differential equations. Okay. And we express that linear system of differential equations by the matrix differential equation, the derivative of the vector x with respect to t equals a times x of t. And incidentally, this can be, oftentimes this will be written as x prime equals ax. They'll suppress the t. Okay, so you'll see it a lot. You'll see that a lot written this way. Okay, so let's go to the solution here. So let's see if this eigenfunction is a solution to the differential equation. So what am I going to do? I'm going to differentiate. I'm going to differentiate the eigenfunction with respect to t. Okay, so I'm taking the derivative of that eigenfunction vector. But the vector v, remember, is an eigenvector, and it's a vector of constants, of scale, of numbers. So you learned that you can pull out, when you take the derivative of a function, if there's a number in front of that, the function, you can the number comes out, right? So in other words, you know, like if you have the, I mean, this is like you have the derivative of, you know, 2, you know, let's say you have the derivative of 1e to the 3t. Hold on, let me show you what I mean here. Just give me a moment here. So if you're taking the derivative as an example of the vector, say 3e to the 2t, and minus 4 e to the 2t. That's just going to equal, right? That's going to equal 3. Hold on here. 3 times 2 e to the 2t times negative 4 times 2 times e to the 2t. Right? And we could write that as the vector 3 and negative 4. Okay, 3, negative 4 says your eigenvector. Well, I'm trying to justify, Matthew, this part here of the proof where we pull out that vector v. Okay. So that is simply this. So what happened was, what I'm trying to do is, how do we go from here to here? Well, you see here how we have the 3 and the negative 4 in front of the e to the 2t? Well, if you differentiate that vector, you're going to get, for the first entry, 3 times 2 times e to the 2t, and for the second entry, you're going to get negative 4 times 2 times e to the 2t. But you could write this vector here as the vector 3, negative 4 times the derivative of e to the 2t, which is what you have here. Like, does that make sense? Does this example help you see it? Maybe give me a few thumbs up if it helps you see it. Let me see. Why did lambda, Divahar's good. Why did lambda get? Oh, okay. Well, let me go. All right. So we'll go down. But our work, Divahar's good. She liked the example. Does anybody else like this little? Is this helpful for anybody else to? Okay. Good. 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 All right. Well, now, so we're here now. We're here. We're here. The derivative of e to the lambda t d with respect to t is lambda times e to the lambda t. And then I can just rewrite the vector v times lambda as lambda times v. But why is lambda v equal to a times v? Solon was asking that. Why can I substitute for lambda v? Why can I put in a times v there? Why can I do that? I just replace lambda v with the matrix A times v. Why can I do that? What do we know about lambda? What do we know about the vector v? Lambda is we're saying here that A times v equals lambda times v. When's that true? That's true when lambda is an eigenvalue of A and the vector v is on the vector v is what of A? Lambda is an eigenvalue of A. Good Robin, so good Solomon and good Robin, and the vector V is its corresponding eigenvector. Hence, we get here. We get to this step. But what is V times e to the lambda t? That was by definition x. That's our eigenfunction. So we took the derivative of the eigenfunction and we got a times the eigenfunction. That means that the eigenfunction, which is v times e to the lambda t, is a solution to the linear system of differential equations. That's what it means. So now we know how to find a solution to a linear system of differential equations, and it involves eigenvectors and eigenvalues. Oh my gosh, here we see it again, right? Eigenvalues and eigenvectors must be pretty important, right? How many think that's absolutely cool? Okay, great. Great. Well, we will, I'm happy about that. Christy's mind blown, amazing. So we're gonna, you know, on Thursday's class then, actually solve a linear system of differential equations, but at least we know how to get a solution. And we'll take it and so we'll look at an example on Thursday. We'll continue section 5.7. Thank you for staying a little bit extra time, class, for this. And if there are any questions, if there are no questions, I'll stop the recording.